Going to continue on here. So we've been grab that pen maybe. We've been talking about obviously organic chemistry here, alkenes and alkynes last time, and we finished up sort of talking about reactions that alkenes go under. And remember, alkenes have a double bond, and that means that they are unsaturated, along with our alkynes, which has a triple bond. And typically, alkenes will go under what are referred to as addition reactions. And addition reactions are different than sort of substitution reactions that we saw with our alkanes. In an addition reaction, we basically are just going to add two things in. And where it happens when we're dealing with our alkenes is it always happens pretty much at our double bond. And that's pretty much as you'll see as we go through the rest of these chapters here and organic chemistry. Pretty much that is where most of the reactions take place, is near that sort of functional group for that particular compound. Now, as we talked about last time, pretty much it always sort of works this way. And the way it works is at the current way that the carbons are bonded together, they pretty much have four bonds, which means if you wanted to add something there, there's frankly not enough room to do so. They will end up with too many bonds. So if you're going to add something, the first thing that always happens is this double bond does need to become basically a single bond. And what that's going to do is basically open up room for those things that need to come in to basically attach. So as I talked about before our last time, when you're drawing sort of these products of these reactions, you kind of always have pretty much the answer staring at you on the left-hand side of the arrow. You just need to adjust it accordingly to what is going on. So in this case, everything else remains exactly the same. Nothing else changes. We're just going to make that double bond into a single bond. And what that's going to do is allow room for each of these things basically to add in. And they're going to add in to opposite carbons. So one's going to go to each of the carbons. And that will add in our guy here as well on this side. And no matter if there's a lot more carbons attached, if there's other things attached, that's pretty much always the situation in these separate reactions. We make our double bond into a single bond and basically put one thing on one carbon and one on the other. There's really kind of two types of addition reaction. There are symmetrical additions. And in symmetrical additions, you're basically adding the same thing, which means, frankly, you can't necessarily mess it up per se. You might be adding H2 or two hydrogens, which is a hydrogenation reaction. Maybe you're adding two bromines, maybe two chlorines, or whatever it may be. So in these type of reactions, there's really no difference in terms of where you put anything, because if you throw a hydrogen on the left or the right, you're basically just put the same thing on both carbons. So it doesn't really matter. So the only thing that does matter is, again, here, always in these situations, one should go to each carbon, not both to the same carbon. So always opposite carbons within a double bond is where you do that addition. There's unsymmetrical addition reactions. And when you do an unsymmetrical addition reaction, you're typically adding hydrogen and something else, some type of negative ion as well. So the common sort of hydrogen and something else is water. And when you add water, you can think of water as like H and OH. And that's essentially what's being added in this particular case. You got something like HBr, that's an H and a Br going to be added, or like HCl, be like an H and a Cl being added. Again, here we're going to put the hydrogen on one carbon and the other guy there on the other. Now, there can be a situation when this occurs that it does matter sort of where you put things. And that is what happens when there's a difference. For example, hydrogens on this guy, I think. So let's just say we wanted to do this and we're going to add water here. And again, you could think of water being added as like an H and an OH. Now, when we have a situation where we're going to do this reaction, it's still going to work the same way. It's still going to be pretty much right there is the most important part. And still, we're going to just make it into a single bond. So really, you should almost not think about it too much and think yourself out of perhaps the right answer. So you should just copy exactly the way it is. Again, nothing should change other than the double bond becomes a single bond. So again, you pretty much have 95% of your picture by just copying what's there on the left-hand side. Now, in this particular case, we're going to add hydrogen to something, and there is an actual difference as to where the hydrogen should end up versus where the OH in this case should end up. And it has to do with when we look at the original carbon-carbon double bond, and we look at the carbons that are basically there, we're looking at how many hydrogens does each of these carbons have directly attached to it. So this guy's got one hydrogen directly attached to it. The carbon on the right-hand side has 1 and 2 hydrogens basically attached to it. In this situation where there is a difference in the number of hydrogens on the 2 carbons in the double bond, that hydrogen that you're adding will end up going to the one with the most hydrogen. So the one with the most hydrogen will actually get the hydrogen. And then obviously the OH would go to the other one. So in this particular case, we would actually put our H here, and we would put our OH over here. And this is what is referred to as a major product. And when you draw things, you typically want to draw the major product. The minor product would be, frankly, just the opposite. You put the OH on the other one and the H on that one on the left-hand side. But you should always shoot for the major product in this particular case. By the way, in this case, when you add water to a alkene, you go from an alkene to an alcohol, where you have a functional group of OH. So you go from an alkene to an alcohol by adding water to it, and you get that. Just like we saw, if you add an H2 to an alkene, you go from an alkene to an alkane. Basically, take out the double bond. This is what is known as, I'm gonna butcher it, Markovnikov's rule. So as Markovnikov's rule is that one where the hydrogen will end up at one that had the most hydrogen to begin with. That works for anything which is unsymmetrical, where you're adding a hydrogen and something else. That's not a hydrogen, obviously, in this case. Any questions on us up there? All right, so the only thing you should change is make your double bond into a single bond. So if you do that without even thinking, all you have to do is just copy double bond, single bond, everything stays the same. Nothing else changes. And now by making that double bond into a single bond, we now have room. And in an addition reaction, one goes to one carbon, the other goes to the other carbon. And in this case, since they are both the same, you can't hopefully mess it up unless you put them all on the same carbon, but we should put one on each carbon, and that is how it works if you're adding 2 of the same thing. And this is sometimes referred to as a symmetrical addition, and that's just a fancy way of saying we're just putting the same thing on both carbons. There's also unsymmetrical additions, which works the same way. If you have an unsymmetrical addition, it doesn't matter how many carbons you got going on there. It doesn't matter if you got 400 on each side. You got that double bond. It's pretty much where it's going to happen. We're going to look at this, and maybe we're putting 2 different things on. Now, when we do this, we're still going to just draw it exactly the same, but turn our double bond into a single bond. At this point, we now can have room to put one on one and one on the other. So That is pretty much your addition reaction. This is what's sometimes referred to as an unsymmetrical addition, and you're basically adding two different things. Now, there are certain rules that you should follow when you're doing an unsymmetrical addition reaction, and we'll talk about them in just a second. But when you're doing a sort of a symmetrical addition reaction, it doesn't matter. You just slap the same thing on each of the carbons. By the way, the reason this is here, that is what it means when they say you buy something that has been partially hydrogenated. Yes, so you turn your double bonds into single bonds. You go from an alkene to an alkane in this case when you add hydrogen, and it actually changes the properties, and that's how you get things like margarine, oil, and butter, and all those type of things, depending on how many double bonds you get rid of. So in an addition reaction, we can add something like hydrogen, which is known as a hydrogenation reaction, and basically we're just basically putting the hydrogens back that we took away. So if you remember, in order to make a double bond between these two carbons, we had to remove two hydrogens basically, right? And we end up with this. And that means that if we were going in this direction, we're just going to frankly put the hydrogens right back on in the spot where we took it away and make it a single bond. And that's what's known as a hydrogenation heading in that reaction. You could also add water, which is known as a hydration reaction. And we'll talk about that here in just a second. You will actually get an alcohol versus you'll get an alkane in this case. So let's take a look at a hydrogenation reaction. So let's just have something like this, perhaps. I don't know. We'll do that. And we'll do this. And we're going to add a little hydrogen, which is H2, right? And again, here, you usually will need some type of catalyst. So maybe you'll see something up here as a catalyst to do this. Now, in this particular case, although there's a lot of stuff drawn there, right? The only place I should really focus in on is the double bond. So this is the only thing that I should focus in on. And I should draw it exactly the same. I shouldn't change anything except double bond to a single bond. So once again, you pretty much have your product that you need to draw already drawn for you. Just copy what's there. So I'm going to do that exactly the way it looks. Again, I'm not going to change anything until I get to that double bond. Everything's going to be exactly the same. No funny things happen like rings form or things of that nature. I'm going to turn my double bond into a single bond, and that's an important part, right? Because that's going to allow room for things to come in. Everything else will still be the same in this case. Now that I did that, I pretty much have room for hydrogen to go there and one to go there. Just like when we make the double bond, we take a hydrogen from each carbon. When we put it on, they go to opposite carbons. So we'll put a hydrogen there and a hydrogen there. Again, we go from an alkene, which is 1, 2, 3, 4, 5, a little 1 pentene, to an alkane, which is pentane in this case, right? So we go from an alkene to an alkane, and this is what is known as a hydrogenation reaction. By the way, you could also do this with like Br2, Cl2, any two things that are kind of the same. So it works the same way. So if I had something like this, and I want to add, say, Br2 to it, why don't you draw what you should get? Works the same way as the hydrogen. Once again, that's only the area that I should be concerned with, and we need to make room for this. So everything stays the same. So do yourself a favor and just copy what's on this side here. So I'm going to copy it. Again, don't do anything fancy with it. Just copy what it is. And we're going to go this way. Again, we're going to turn that double bond into a single bond there. And a little bit of this. And now, obviously, where I made the single bond, I now have room for Br2, which is basically two BRs. And because they're both the same, it doesn't matter where you put them. We'll put a Br there and a Br there. And again, we go from an alkene to an alkane in this case. Any questions on that there? So we have 1, 2, 3, 4, 5. So that's a 2-pentene in this case, to a 1, 2, 3, 4, 5, to a pentane, a 2, 3 dibromal, right? Pentane in this case, right? As we have those guys. Any questions on that? So these both would be considered what is sometimes referred to as symmetrical addition, because you're essentially just adding the same thing to each carbon. So it doesn't really matter really where you put the bromine in each case, or chlorine if you do it with chlorine, or if you do it with hydrogen, it doesn't matter as long as you again put them on opposite carbons where the double bond was located. Now with unsymmetrical addition, a lot of times what we add, and again, these are all symmetrical addition. So with unsymmetrical addition, we typically will add two different things. So with an unsymmetrical, we're going to add two different things. And there are some rules that we sort of follow when we do these things. And it usually involves the addition of a couple of things: water, or something with hydrogen like HBr, HCl, hydrogen, and something else, basically. When we look at water, by the way, and when we add water, the way that we kind of look at water in this sort of addition is we look at water as being an H and an OH. That's sort of how we think of water, and that's sort of how it's going to go on. So in this case, we would be adding a hydrogen and an OH in the case of water. In the case of HBr, we would add a hydrogen and a bromine, HCl, hydrogen, and a Cl. So those are the two things that we're adding. So unlike H2, where they're both hydrogens, unlike, say, Br2, where they're both bromines, here we're adding two different things. So there is a rule that we follow, which is known as Markovnikov's rule. Don't ask me to spell it with an M. Rule. And really, he did a lot of work with electrolytes. And what he found was there is sort of a pattern that happens when you add hydrogen and something else to a double bond. And the hydrogen will end up, the hydrogen part that you're adding, so this guy, or this guy, will end up at the carbon that had the most hydrogen to begin with. Now, obviously, if there is no difference in the amount of hydrogens, it doesn't matter where you put it. You can put it on either one. But if you look at the double bonded carbon, and one of the carbons in that double bond has more hydrogens than the other to start with, I think they're redoing next door. It looked like they were pulling some wires there. So it looks like when you have that situation, the hydrogen should be added to the carbon that had the most hydrogen to begin with. So let's take a look at a situation where it doesn't really matter. So obviously, if we had something like this, and we look at the double bond here, each of these carbons has the same number of hydrogens. So it really doesn't matter. Let's add water to it. And again, when we're adding water, we're going to add it as HOH in this case. So we're going to follow the exact same thing that we did before, which is we're going to break the double bond and make it a single bond. But everything else, again, is going to look exactly the same. So I'm just going to redraw it like I have it on the other side, exactly the same, but with a single bond in this case. And at this point, what we're going to be doing is adding an H and an OH. In this case, because there is no difference in the amount of hydrogens, you could put the H on whichever side you like, and you can put the OH on whichever side you like. So for example, I'm going to put the OH here and the H here. In this case, this is what is known as a hydration reaction because we're adding water. And this goes from an alkene to our friend, the alcohol. The alcohol is another organic group that has the OH group attached to it. And by the way, this would be ethene. This alcohol here would be based off of that, and it would be known as ethanol. You put OL at the end for alcohols, and it's still based on the number of carbons. Now, you may be saying, would I get something different if I put it the opposite way? And the answer in this particular case is no. If you put the OH on the left and the H on the right, it would still be ethanol in this case, and it would not make a difference. Same thing if we had something like this and we added HBr in this case, right? So same thing, we're going to break that double bond into a single bond. And now we're going to put a Br here and an H here. And in this case, we will end up with an alkene, and we'll end up with an alkane that has basically a halogen on it, or a haloalkane is sometimes referred to because it has a halogen on it. The guy over here is ethene. Over here, this would be bromoethane, right? Would not need a number here because that would be carbon number 1, right? Where the bromine would be at. But if I put it on the other side, that would be carbon number 1, right? So it would be the same name regardless of which way you do it. So in this case, it doesn't really matter in terms of the hydrogen. When you put these guys in here, you'll get really the same one. Doesn't matter where you put the hydrogen or where you put, the OH or whatever else is attached. First off, any questions on this? Now, when it does make a difference, we do want to make sure that we sort of put it in the correct way. So let me draw something where maybe it will make a difference. So let's go with yeah, hydration is a type of reaction where you add water, basically, and that's why it's called hydration. Just like hydrogenation is when you add hydrogen, basically. Yeah. So if we have something, let's do let's do this. That should work. That we'll do this, and we'll do this. I'm going to add my water here to this, which again is going to be H, and OH is basically what I'm going to add. All right. So although it may look a little different, there's a few extra things attached. The only place I really should be concerned with is the double bond still, right? So we got to make room for everything. So once again, although it may look different, there may be more stuff there or less stuff. We're still just going to focus in on there, and we're going to make it into a single bond. Once again, I highly recommend the copying of what's there because that's pretty much the answer. So I'm just going to draw it underneath so I have a little bit more room. I'm just going to copy it exactly the same. And once again, the only difference I'm going to do is turn my double bond into a single bond in this case. And we'll do this, yeah. I now have a location where I can put the hydrogen and the OH in this case, right? Because that's what water is going to add. So I'm going to redraw this one more time the exact same way, and we're going to talk about the two options of what could happen in this situation. So I'm just going to redraw it once again, exactly the same. Option number 1 is I could lay my hydrogen over here on the left and my OH on the right, right? So that is one option that could happen. Option number 2 is the opposite of that. I could lay my OH over here and my H over here. That actually does give me, in this case, 2 different alcohols. These are both alcohols in this case. So to see that we do have two different alcohols, let's actually talk about how you name these. So we'll talk a little bit here about how you name alcohols. Surprisingly enough, you name alcohols the exact same way as you name everything else, which means we're going to look for the longest carbon chain. And in this case, it does need to contain the OH group, which is the alcohol. So in this case, the longest carbon chain that has the OH group is how many carbons? It is 4 carbons. And we dropped the last part of the name and we put OL on it. So 4 carbons is butanol, OL, instead of butane, right? And that tells us that it is an alcohol. Now, alcohols are very similar in the sense of how you go about naming them, very similar to what you do with double bonds or triple bonds, which is we give the location of the double bond, right, or the triple bond, if there is more than one possible place where it could end up. That happens, by the way, with alcohols, too. We need to give the location of where the OH group is. And that happens with alcohols when you hit about 3 or more carbons. So when you hit 3 or more carbons, you do have to give the location of where the OH group is, just like we kind of do with double bonds and triple bonds. Just like double bonds and triple bonds, when you move to an alcohol, it is the OH group that is the most important in terms of numbering. So the functional group is always like the most important thing. So the OH group here is the most important thing. We want to give it the smallest number. So for my guy up here on top, which way would numbering give me the OH group the smallest number? We would want to go right here to left, right? 1, 2, 3 as well. I feel like I'm lost. There is 4 carbons there, right there. Thank you. There it is. I have the butanol. That was right, and I just did miss that carbon up there. So that would be 1, 2, right? There we go. 3 and 4 in this case, right? And the other way obviously would be 1, 2, 3, and 4. So starting up there on top and coming to the left there is going to give us 2-butanol in this case, right? Which would be this name. Now, when we go to the bottom guy, we also still have 1, 2, 3, 4 carbons, which is butanol. In this case, though, if we number 1, 2, 3, 4, or if we go 1, 2 in this case, which way should we go in this case? Yeah, we should, right? It's going to give that OH the 2-butanol, right? So that's 2-butanol. And in this case here, we ended up with 2-butanol as well coming that way. So I feel like something not right here. 1, 2. It is not the best choice in this case. So it is not the best choice. It's my fault. I did a bad drawing there. We did end up with the same guy both ways, which is really bad for what I was trying to demonstrate here, obviously. The reason we ended up with the same guy is, how many hydrogens does this one have? And this one has? Have the same number, so that really defeats the purpose of what I was trying to do there. So here, as you can see, it doesn't make a difference, right, as they have the same number of hydrogens. Let me actually fix this a little bit here to make it what I was trying to do. It's all that banging. I'm just going to blame it on. How's that? I'm just going to blame it on all the banging. All right. So obviously there we have the same number of hydrogens in the double bond. So like we saw previously, it doesn't make a difference. Let's actually do one where it will make a difference here. All right. So what I'm going to do here is I'm just going to drop another. Let's just do this guy here. Let's just put a methyl group there. Now they have different numbers of hydrogens. There we go. Let's try this again. All right, we're going to redraw this with the 2 options. And if I didn't screw this up for the second time here, this will definitely, hopefully, have some different things happening. So once again, I'm going to single bond it up here. We're going to go this way and this way. There we go. And one option obviously would be to put our hydrogen there and our OH there. Now we can also do this. And one option obviously would be the opposite there and switch them around. So just do this is different color here, H, OH, and then we'll do OH and H. All right, let's try this again. Let's try the naming thing again here, see if we do better. At least I do better. I'm screwing it up here. You know, it's just going to be a big edit, like hello and goodbye is going to be the whole video this time, I think. All right, longest carbon chain now, what do we got? It is still 4 in this case, right? So you could go straight across and get 4. You go straight across and then up, right, and get 4. So we'll just go straight across here, which is 4. That contains the OH group. So the base of my name here should still be butanol, right, as it is 4 carbons and an alcohol. The OH group should be carbon number 2 in this case, right? And that's going to give me 2-butanol in this case, right? Now, we also have a methyl group here, right? And that methyl group would be at carbon number 2 as well. So this would be 2-methyl, 2-butanol would be the name of this. Any questions on that? I'm going to really hope we get a different name on this one. Let's see. Longest carbon chain on the bottom one is still 4. Let's go straight across there. And that is going to still be butanol. OH group is at carbon number 2, right? So that's going to be 2-butanol. And that means, though, my methyl group in this case is at carbon number, thank goodness. All right, so that is a 3-methyl 2-butanol, right? So we now have 2 different things after 40 minutes of the same slide. We do have 2 different things in this case. So there is a difference here because of the number of hydrogens, right? So they don't have the same number of hydrogens as we saw in the previous examples. Now, based on Markovnikov's rule there, the hydrogen should end up at the one that had the most hydrogens to begin with. And which one had the most hydrogens to begin with? The carbon on the left, right? This guy had 1 hydrogen. This guy, after I fixed it, had no hydrogens. So the proper one that you should draw really is this guy here. This is what is sometimes referred to as the major product. Why does say again? Because that's the main thing. That's like the main compound. So the functional group here is an alcohol, which is the OH. So always like the name of the functional group, sort of longest carbon chain, goes at the end. So like how we had like butene, that was like ENE was the double bond guy. In this case, it's the alcohol. So that becomes the base of the name. And it's still based off of the alkane name, right? Because it has 4 carbons. So it's based off of butane. But because the functional group here is an alcohol, it becomes butanol, OL, at the end, and that becomes the end of the name there. Yeah. Other question? Yeah.
When they both have an equal amount of hydrogen,
yeah.
The name for an alcohol could be the exact same.
It would be the exact same, like my mess up that. Yeah, like my mess up I just did there. Because of the addition, it won't matter pretty much which way you go. You'll probably end up with the same thing, no matter which way you go in that case, because it is sort of symmetrical in that sense because they have the same number of hydrogens. You're just kind of putting it in there. In most cases, it should end up that way. This guy here would be what is referred to as the minor product. And in most cases, you usually want to draw the major product. So when we have a difference like we had here, we want to put the hydrogen on the one that started with the most hydrogens, and the other guy will go to the other carbon. So hydrogen always to the one with the most hydrogen. If it doesn't make a difference, as we saw in those few examples, it doesn't make a difference in terms of where you put it. Let's try one more here. Dare I try it? Let's see. All right, so what do you get here? In this case, if I finish some hydrogens here. All right, so draw the product that you should get here. Okay, so let's take a look. Remember, when we're adding water, it's going to be an H and an OH. So we want to look at our double bond. All we're going to do again is just turn it into a single bond here. So we're just going to kind of do this move here. And at this point, once we do that, we do want to sort of analyze our carbon-carbon double bond where it's at. And we do have differences in terms of the number of hydrogens in this case. We have 2 on the right and none on the left, right? That means that the hydrogen should end up on the left or the right. Should end up on the right, and the OH here should end up over here. What do we think the name of this thing is? I feel like you're just saying names. Are you saying it? All right. Longest carbon chain here is, so I think we got 4. Let's see, we got 1, 2, 3, and we could go 4 straight across. We could also go up to get 4 or down to get 4 in this case. So the base of our alcohol here, right, is going to be butanol, right? So I think that's maybe what you said. Yeah, butanol. And we do need to give the location here of the OH group because it's 3 or more carbons. So as you correctly said, they're going right to left in this case. Going to give that OH group again the smaller number, which would be 2-butanol. That means that we have a group here, we have a group here, and we have a group here. Uh-oh. Here I was going off of your name, but yeah, all right, we'll continue on then. We have 2 methyl groups, right? So we got a little perhaps dimethyl action happening. Yeah. We also have a bromol happening. And because we locked in the numbering for our OH, that is the numbering for everybody else, right? So that means that's a 2-bromol, right? And that's actually a 3-3, right? We want to go alphabetical, which means we should go with the bromol first there, yes. So that's going to be, I'm going to start way over here, I think. It's 2-bromol dash 3,3 dimethyl dash 2-butanol. That is a mouthful. That's a question on that there. By the way, when we look at alcohol, since we're got a little alcohol this week, perhaps in lab, doing the alcohol experiment, I guess is a better way of referring to that, hopefully. We can also classify our alcohols, right, as primary, secondary, or tertiary alcohols. So that's why we got one up here: primary alcohol, secondary alcohol, or a tertiary alcohol. It is kind of similar to what we've done before. What we want to look at is actually the carbon that has the OH group attached to it. So that would be this carbon in this case. And we want to look at how many carbons are directly attached to that guy. How many are directly attached to that guy? That would then make this what type of alcohol? This would be a secondary alcohol, right? Because that. We saw, I think, ethanol earlier, I think, which looked like this. We would look at this carbon, right? And that carbon that has the OH group is directly attached to how many carbons? 1, which means this would be a primary alcohol. While we're at it here, let's go for the trifecta here. We'll see how we do. This carbon is attached to how many carbons? This would be a tertiary alcohol, yeah? Out of curiosity, what would that alcohol name be if that is true? What do we think? Longest carbon chains, how many? Keep going. It is 3, yeah, right there. That is 3 carbons in a row, yeah, with an OH group, which means that is based off of propane. So that now becomes propanol, right? Location of the OH group in this case, because it's 3 or more, is that carbon number 2, right? So that is 2-propanol. If the methyl group wasn't there, that would be rubbing alcohol or isopropyl alcohol. But in this case, because there's a methyl group at carbon number 2, this would then be 2-methyl 2-propanol in that case, right? And that would be the way that you would name that alcohol. Questions on that? A little alcohol preview-ish. Any questions on that there? Back to the addition reaction. Any questions on the addition reaction as we went on a tangent, I suppose. All right, so addition reactions, pretty much just remember double bond, single bond. One goes to each carbon. The only thing you got to worry about is when you're adding hydrogen and something else, if there happens to be different numbers of hydrogens on that carbon-carbon double bond, hydrogen ends up at the one with the most to start with, yeah? Again, a hydrogenation reaction means you're adding hydrogen. You go from an alkene to an alkane. Hydration reaction, you're adding water, which means you go from an alkene to an alcohol here. Any questions on that there? Let's take a look at some of these here. So here's our hydration reaction. As I mentioned before, I'm not going to be too concerned with the catalyst, but you might see them in some books and problems. They're up on top of the arrow. A catalyst, again, is something that will speed up the chemical reaction. It really doesn't play a role in sort of what you're drawing. It's just there functionally when you actually do the reaction. So for us, you don't have to worry too much about the catalysts that are up there, but if you do see stuff up there, it really won't do anything to affect your drawing in most cases. You could kind of ignore it. Here again, hydrogenation, going to pop that double bond into a single bond. Everybody gets a hydrogen. So let's write the equation for the hydrogenation of 1-butene. So let's start with 1-butene, which is 1, 2, 3, and 4. 1 would be right about there. And then everybody else is hydrogens, right? So we'll do that. We'll do that. We'll do that. And then I'll let you draw it then. So draw the product that you get there. All right, so let's take a look. If it helps you could draw out all the hydrogens, especially around the double bond. It might be helpful to just kind of draw those guys out so you can kind of see what's going on here. We'll go one more here. We're going to add our hydrogen, which is 2 hydrogens. This is really a symmetrical addition, which means you don't really have to worry about much on this guy other than get rid of the double bond pretty much. So once again, we're just going to copy it exactly the same, turning that into a single bond in this case. That's going to allow room for everybody to come in. And because, once again, we are adding, in this case, basically 2 of the same things, you really can't mess it up unless you put them all on the same carbon. So as long as you go opposite carbons, you should be in good shape in this case. And again, we make basically an alkane here from our alkene in this hydrogenation reaction. As I mentioned before, that actually will make things more solid in terms of like oils to margarine and versus butter. It depends on how many double bonds and stuff like that. So sometimes you'll hear things, like I said earlier, are partially hydrogenated. It just means it went through, added some hydrogen, got rid of some double bonds, and it changes things like their sort of physical attributes, like they become more solid when they're more single bonded versus, say, double bonded and stuff like that. Did we? I feel like almost at the end we maybe did it. Yeah. Okay. Then maybe we did this one. Then we'll go to the next one. How's that? I like it. All right. So I think we were also talking about towards the end here, hydrogenation of oils. And again, as I mentioned, I think at the end there as well, this is what is sometimes referred to as being partially hydrogenated. They add hydrogens to it. It actually increases the melting point because it allows really the carbon chains to sit much nicer with each other. We'll talk a little bit about this when we talk about fatty acids in the lipids chapter towards the end. But what happens when you have double bonds in this part of the molecule is it actually creates kinks in the chain. So instead of things sitting really nicely with each other, they kind of kink out all these things, and you end up getting not great interaction sort of happening, as opposed to when you kind of turn that thing into a single bond. This guy stays pretty straight, which means if you have another guy coming in there, they're going to be able to kind of line up really nicely with each other. And that really does sort of change sort of the properties of those type of things. Let's try these, which I don't think we did. So let's try these guys here. And let's also do, okay, so let's take a look and see. So remember that when you are going to draw these things, sometimes people freak out over the drawing part of it because I'm not really sure what I should draw. And again, sometimes people do kind of weird things and draw things weirdly and stuff like that. So trust me when I say in this class, pretty much what you start with is almost what you end with. Just small little changes is what you should make. So again, you pretty much have the structure that you need. So I just redrew it up here so we could kind of isolate the double bond. And the reason we're going to isolate this double bond is, again, that's pretty much where everything's going to happen. And that's the thing that we need to turn into a single bond. So really, you can pretty much just jam right through it and copy exactly what's over there. And again, all you essentially got to do is turn that double bond into a single bond. And again, nothing else changes. So don't get fancy with it or funky with it or anything like that. Don't turn it into a ring or anything of that nature. And then at that point, we now have room for, in this case, our hydrogens. And again, they go one to each of the carbons. So we would just slap a hydrogen there on each of those. And then we would be in business at that point. Yeah. Any questions on that one there?
Say that if you left it CH and just remove the double bond and added a hydrogen.
Yeah, so I drew a little combo of condensed and expanded here just to see the part that changes. But you could have, if you're asking, could you just done this? You obviously need to add the hydrogens to each of those and to H2s, and that'd be fine. Yeah, that'll just be the condensed structure there. Other questions on that there? All right, same thing here. This is a cyclo structure with a double bond. So once again, that is the only thing that's going to change. And by the way, it's not going to open up and do anything weird like that. It's going to stay closed. And we're just going to do the exact same thing here, which is pretty much just copy what we got going on there. Except in this case, we're just going to turn it into a single bond, which means don't draw the double bond, right? By doing that, and by the way, to start with, there is one hydrogen at each of those spots. Now that we got rid of the double bond, we make room for the hydrogens that we want to add here. And again, we would add, just to show it perhaps, we'll just show that we put the hydrogens on, even though you don't really need to. If you drew this the picture originally, it implies that there's two hydrogens there and that you put kind of the hydrogens on there as well. Other questions on that? So again, in this particular case, because it is sort of line structure, you actually could just draw it like that, and it would imply that they would have the two hydrogens sort of there. Any questions on that there? All right, top one, we're adding water, and water here is going to be our H and OH, and we're going to, again, still only focus in on our double bond, which is right here. And nothing else is going to change. So we can, again, just copy it directly like it is. I'm going to go with a, where am I going to go with that? I can go up top. I can go over here. CH3, C, we're going to make that into a single bond. We will still have the CH3 on the bottom. We will still have the hydrogen up there. We'll have our CH2 and our CH3. So frankly, I'm just copying what's there. Now I have room, and I'm going to add an H and an OH. And in this case, dare I say, third time's a charm, maybe we're going to follow Markovnikov's rule here, which is the hydrogen should end up on the one that had the most hydrogen to begin with. And in this particular case, it would be our carbon on the right here, right? It had more hydrogens. So that is where, I'll put a different color so we can see it. That is where the hydrogen should add. That means my OH should be over here as well. Yeah. And again, that would give us our major product in this case. Any questions on that? think I did not bad. I think I forgot the V there originally, but what you can do. Any questions on that there? So you do need to be able to obviously draw the products here if you're just given the front part and draw correctly, everybody coming on correctly. All right, let's see. We talked about our hydration reactions again, creating our alcohols. So why don't you do this one as well? Why not? Okay, so let's take a look at it. And again, if it's helpful to you, I'm just going to kind of draw out everything around the double bond because I know that's kind of where everything's going to happen. So it might be helpful just to kind of visualize what's happening. If you want to draw out all the other hydrogens, you can as well. So we'll have that going on. We've got a little double bond action. We've got carbon and a couple of hydrogens. And here again, we're going to add our water. So once again, we're going to focus in on our carbon-carbon double bond. And once again, that is going to be really the only thing that's going to change here. And because we're adding hydrogen and something else, sort of an unsymmetrical addition here, we do want to look at the carbon-carbon double bond, and they actually do have different numbers of hydrogens. So we know that in this particular case, the one that had the most hydrogens to begin with is over here. And that is where our hydrogen should end up when it's all said and done. But before we do that, we could get to the drawing part, which again, I'm just going to copy. So CH3, CH2, carbon, hydrogen, single bonded, carbon, hydrogen, hydrogen. So in a matter of 5 seconds, I have pretty much 99% of the molecule drawn for me by just copying what was there to begin with. And now we're just going to put everybody in the right spot here. So we'll lay up a hydrogen there and we'll lay up an OH right there. And we'll end up with something like this as well. Now, if you were going to go full condensed, obviously you would bring the hydrogens back in and leave the OH as the only thing kind of hanging out there attached. Any questions?
So the OH goes where it's the most carbon.
The hydrogen should go to the hydrogen should go to the carbon that started with the most hydrogen to begin with. So we're looking over here. So this carbon has 2 hydrogens. And this carbon originally in the double bond has 1. So the hydrogen should end up at the carbon that had the most hydrogens to start with. So that's the guy on the right.
For the test, is that okay, or do you want us to put it in the condensed version where the H's?
I'd be fine if you drew it like that, to be honest with you. I'm okay with it. But if you want to put it into condensed, or if you want to expand out all the hydrogens, you can. As long as the instructions doesn't say specifically like, draw it in a condensed or something like that. So again, I'm just kind of drawing out the double bond area so you can kind of see where everybody ends up. But again, if you were going to just kind of turn it into a condensed, it would look something like this. And then you'll have your OH hanging off of there, basically. So it looks something like that. Other questions? So hydrogen to the carbon, most hydrogens, other guy to the opposite. Yeah. Yeah. Yeah, so I would expand it, or you don't have to expand it. It's up to you, whatever you want to do. But just so we're clear, when we're talking about most hydrogens, we're talking about directly attached to that carbon. So just directly attached to that carbon, not right straight bonded to that carbon is what we're talking about. So even though, there's a bunch of hydrogens hanging out over here on the left, we're not talking about those hydrogens or anything like that. We're talking about the ones that are directly attached to the 2 carbons that make up the double bond. Yeah, the one on each side. Yeah. Other questions? Okay. All right. So let's then talk about another class of organic compounds, which are aromatic compounds. Aromatic compounds have what we like to call in organic chemistry a benzene ring. And this is a benzene ring. It's a 6-carbon ring with 3 double bonds. You can also draw what is referred to as a resonance structure, like we talked about, I think, in Lewis structures, where the double bonds head in the opposite sort of 3 guys. That also means, as you can see here, these are all hydrogens. There's one hydrogen at each of those carbons because of those double bonds. I would say for simplicity in books like ours, sometimes they will draw the benzene ring, which is a circle kind of in the middle. And the circle indicates that those double bond electrons are delocalized, they're moving around, which is basically what the resonance structure means. They can be on one carbon or the other. So sometimes you'll just see it drawn with kind of like a circle in the middle. It still has the 3 double bonds happening there. It's just sort of a shorthand that's sometimes used for the benzene ring. So this is not, by the way, this is not the same as this, because that is what? That is cyclohexane, right? So that's a cycloalkane. That is not a benzene ring. By the way, if you have that right there, what I just drew is cyclohexene, also not a benzene ring. For it to be a benzene ring, you need the 3 double bonds. Was maybe the question that was asked. Yeah. So for it to be a benzene ring, it has to have those 3 double bonds in it. And it will look either with the 3 double bonds drawn out, or probably a lot of times in our book and places here, you'll probably see it more drawn again with that little circle sort of in the middle, and those represent benzene rings. So those are different things, even though they're kind of look the same. And they're different because, again, because of the presence of the 3 double bonds means that the benzene ring only has, for example, 6 hydrogens, and something like this has actually 2 hydrogens at each of the spots all the way around. And obviously this guy has 2 hydrogens at each spot, except for where the double bond is, he's got 1 hydrogen happening there as well. So they have different numbers of carbons and hydrogens, and they are different things. So one of the problems that sometimes happens is people see that ring type structure and it's always now going to be like a benzene ring always. So it's got to have those double bonds in there, 3 of them, or it's got to have that circle for it to be a benzene ring. And that's what makes it sort of an aromatic compound. Question on that there. Yeah.
Does it have to always be C6H6, or could it be like CnH10?
No, so benzene for the most part is that right there. So it's that arrangement of carbons and hydrogens together, if that's your question. That is
So
basically,
all aromatic compounds are C6H6?
yeah, and they have other things attached to them, but the basis of what it is, almost like the longest carbon chain or the basis of what it is, it has at least that benzene ring in it and stuff like that. Now, sometimes, as we will see, sometimes the hydrogens are substituted out for something else, like something else that we've seen, and it will have a different name or something like that. But the basis of sort of the biggest part of it is that foundation of kind of the 6 carbons arranged with that with the double bonds happening. So I won't say it will always necessarily have the 6 hydrogens because they can substitute out for some other things, but it definitely will have the 6 carbons and basically the 6 hydrogens if something's not substituted out will be in there. So looking at that, these are all, again, versions of what a benzene ring looks like. And like I said, a lot of times we'll kind of see it like that with kind of the circle drawn in there. And again, it still has the 3 double bonds that are happening in the carbon part of it. Now, when we name these guys, we can draw it. And there are certain aromatic compounds that are benzene containing that have some historical type names that people still use today. So for example, this benzene ring that basically has a methyl group on it, that is what is known as toluene. So toluene is basically a benzene ring that has a methyl group on it. You could also just kind of name it like you might think, which is you just name the group and put benzene at the end of it. So that would also be known as methylbenzene because it has a methyl group and it's a benzene ring. So sometimes it's referred to as methylbenzene as well. And this would be it in line structure, right? Our lonely line with nothing at the end of it is a methyl group. So that would be its version of it. If you have a benzene ring that has a nitrogen containing group like an NH2, these are amines, as we'll talk about in a later chapter, another organic type of group. And that is what's sometimes historically referred to as aniline. So if you see like a benzene ring that's got like a nitrogen, 1 hydrogen, 2 hydrogens, maybe some other things on there, that's going to be a form of aniline. If you have a benzene ring with an OH group, that is what is known as a phenol. Sort of like an alcohol type of situation happening here. And again, those are three very common names that are still sort of used, and the sort of historical type of names that are still used today. Now, if we look at this here, we can name this as a couple of things. We have a chlorine group here and a benzene ring. So again, we just kind of name the group and put benzene at the end of it. So that would be a chlorobenzene. Here we do not need to give the location because it only has one thing on the ring. So wherever that chlorine is located is carbon number 1 in this particular case. Now we do have two things on the ring here. And that is now going to be 1,2-dichlorobenzene. Dichloral because there's two chlorines in the compound, just like normal. We use the little prefix. Location 1 and 2 is the simplest way. The nice thing about a benzene ring is there's 3 double bonds, which means you could go any way in terms of numbering. You should always be going probably across a double bond when you're numbering it and stuff like that. By the way, the 1,2 positioning on a benzene ring also has a name that is sometimes referred to as the ortho positioning, or just O for ortho. So sometimes people will use ortho instead of the numbering and call this ortho or O. As it moved, there it is. Call it ortho or O dichloral benzene. And again, if you see something like ortho or O, it represents that you have groups at carbons number 1 and number 2 on the benzene ring. And that's specifically used for benzene rings that have a couple of things attached to it, that sort of ortho arrangement. If our CLs move, we now kind of move from 1, 2, and 3, and that is 1,3-dichloromethane. 1 and 3 positioning on the benzene ring is known as meta, or M. And again, sometimes people refer to this as M-dichloral benzene. And when you see the M or the meta, it's basically telling you their chlorines are on 1 and 3, as opposed to over here where it's ortho, where the chlorines would be on 1 and 2. So those type of numbering or names are also used a lot. And here, if we kind of move our chlorine opposites of each other, it will end up at 1 and 4 on the benzene ring. And as you could probably imagine by now, that also has a name which is known as para, or P. And again, sometimes people will call that P-dichlorobenzene. And again, instead of using the numbering, if you see para or P, it means that they are 1 and 4 of each other on the ring, basically opposite locations of each other on the ring. So ortho 1, 2 positioning, again, specifically for just a benzene ring. If you have something on the 1 and 2 positioning, that is the ortho positioning. Meta is 1 and 3 on the benzene ring if you have groups there. And para is 1 and 4 on the benzene ring. Any questions on that? No. So in order to use those sort of prefixes, it has to be a benzene ring, and obviously you need 2 groups attached on it. So here, if we look at some of these names, we have 3-bromoaniline. So if we take this part here, that is our benzene ring with a nitrogen group on it, which is where the aniline part of the name comes from. And since that's going to be our priority here, that's going to be carbon 1, 2, and 3. And that is where our bromine is attached. So that's going to be 3-bromoaniline. Here we have a phenol ring happening right there. So that is the phenol part of it. And now, because that has to be carbon number 1, if I went clockwise in this case, my groups are going to have larger numbers. So in this case, I can go counterclockwise, again, because there's 3 double bonds. So you will go through the double bonds doing it that way. That's going to give me a 2 for the chlorine and a 4 for the bromine. And again, we still go alphabetical order, right? So that is how we get our 4-bromo, 2-chloral, and again, phenol at the end of it, as that's sort of that one, that historical type names. And lastly here, right about there, that is our toluene that we see. And that means that we have a bromine group and another bromine group, which is 2 bromo groups. And that is where our dibromo comes from. We also have a chloral group as well. And obviously we're going to number, in this case, I don't think it matters which way you go. You can go right or left because carbon number 1 has to be where that methyl group is. So in this case, I think you're going to hit the same numbering no matter which way you go. But we'll end up with a 2 and 6 for our bromine groups and a 4 for our chloral groups. Any questions on that there? So sometimes these are hard to see, especially if there's a lot of other stuff in there to kind of see those kind of historical groups. So you just want to kind of be on the lookout for a benzene ring. If there's an OH there, then it's probably going to be methanol. If there's a CH3, it's going to be toluene. Or again, a nitrogen containing group would be aniline in that case. Any questions on that there? All right, so let's take a look at these. Take a moment and decide for the first one and the second one, what might be the correct name here. And we definitely have this guy right there, which is a benzene ring. So I feel like that's going to eliminate this guy, right? And we have a Cl group attached. So that's a chloral. So that is chlorobenzene, 1 chlorobenzene. Do I need a number in this case? I do not, again, because it's mono substituted, there's just 1 there. So that always has to be carbon number 1, which means we really just need to call it chlorobenzene in this case. Yeah. Any questions on that one? Here we have, we really have a toluene, but that's not one of our choices. So we'll go with kind of the older school here. So we still have a not a methyl, a benzene ring there. So that keeps all 3 of these in check. We do have 1 methyl group and 2 methyl groups, which is a dimethyl. So that's good, right? So now we need to do some numbering. In this case, it really doesn't matter which methyl you start with. We could go 1, 2, and then 3. So it should be 1, 3 dimethyl benzene. That would also be what positioning? That is the meta positioning. So that also could be meta dimethyl benzene or M dash dimethyl benzene. Any questions on that one there? Yeah. All right, so aromatic guys has to have the benzene ring. There's a few historical names associated with the benzene ring that you should be aware of. And obviously, you also need to know the ortho, meta, and para positioning of the groups and stuff like that. Any questions on that there? All right, that is chapter 11. It is chapter 12 time now, I think, officially. There's a bunch of flow charts in case you're a bunch more organic groups we're going to officially talk about. We're going to talk about alcohols, which we sort of touched upon a little bit. We're going to talk about thiols, which is sulfur containing groups. We're going to talk about ethers, aldehydes, and ketones. Oh my, let's do it. So alcohols, thiols, ethers, aldehydes, and ketones. So these all have some different functional groups that we're going to talk about. The functional groups really for these guys, alcohols have the OH group. Thiols have a similar one, but it is actually a sulfur containing group. So it has a sulfur instead of an oxygen. Ethers have a carbon, oxygen, carbon sort of run together as their functional group. Aldehydes have actually a carbon, oxygen double bond and an H. And ketones have a run of at least 3 carbons in the row, and in that middle carbon is a carbon oxygen double bond. So these are the functional groups of each of these organic guys. We're going to go through each of them individually here in this chapter, and we'll talk about obviously their functional groups and what's going on with each of these here. But basically we're getting into some guys that have obviously some oxygen involved here, a little bit of sulfur with our functional groups. So as we will talk about, these groups are again where most of the activity and sort of action happens with these guys in terms of reactions, and it also affects some of their properties based on what groups that we got going on here. So we're going to start here again, looking at our alcohols, phenols, thiols, and ethers, and there's our different groups. So here's our alcohol group. That's our phenol group, which is again really like an alcohol with our benzene ring. There is our carbon, oxygen, carbon arrangement that makes that an ether. That is our thiol group that has our sulfur in there. And depending on what group is present, we do some different ways of naming them. So there'll be some slight changes in terms of how we name them, but most of them will still fall back on those first 10 alkanes that we talked about, and we'll just kind of change some parts of the name as we go through it. So again, our functional groups, in line structure, you will still see usually the functional group sort of drawn. So for example, if you had an alcohol like this, you would see the OH, for example, written. As you can see on the bottom there, if you had an SH written, even with, for example, something like an aldehyde, you would see it sort of incorporated into the line structure. And remember, that would be our CH double bonded O. So they do go sort of incorporated into the line structure. And obviously, as you can see there, doesn't look like much, but that is also an ether because again, there's a carbon, oxygen, carbon sort of happening. So we can incorporate our sort of functional groups into our line structure. I would say like this, most of it is going to be kind of drawn out a little bit so you can kind of see it, except for obviously still we don't draw out the carbons that may be involved when you do it. So let's talk about alcohols, and we talked about as we sort of diverged last time into naming alcohols. And alcohols obviously have our functional group of OH, and it ends in OL, an alcohol name. And that is how we basically name alcohols. So we really take the, come back, our longest carbon chain. And again, it does need to have the OH group as part of that longest carbon chain. And we do drop the last part of the alkane name, and we kind of put OL there at the back end of it. So as we maybe saw there, you know, if we had something like this, we would start with our carbons, which is 2. That is going to be based off of ethane. It has an OH group, which makes it an alcohol. So this is known as ethanol. An older way of naming it, as you can see down here, is call it by its group, and that's sort of the common name, and that's why it's sometimes referred to as ethyl alcohol, which is the same as ethanol, and just like methanol, methyl alcohol. So that's the common name, and as I mentioned a number of times, organic molecules, you know, there's the IUPAC way of naming, which is sort of the official way. There's common names, there's historical names, there's something Joe calls it down the street, you know, whatever it may be. There's a lot of names for the same thing. So again, in here, we're going to try to do the IUPAC name on most of it. If it is more of a common name, we might do ethers, maybe more common than IUPAC way. But most of the time, we're going to be shooting for really this sort of naming of our alcohols. Now, as we also kind of alluded to as well, when there is more than one place where you could put the OH group, you do have to give the number of where the OH group is located. So that sort of happens. I just want to draw something. When we get to, again, 3 carbons in the case of alcohols, because we could have something like this. Could also have something like this. So again, in both of these cases, the longest carbon chain is going to be 3, right? That has the OH group also part of it. So they're both going to be propanol. and that obviously is based off of propane, which has 3 carbons. Now, in this case, we do have the OH group right about there, and we do want to, as we've talked about, give the OH group the priority in terms of numbering. So we always want to give it the lowest numbering. So you could probably see that we would want to call that carbon 1, right? Carbon 2 and carbon 3, which means this guy would be 1-propanol in this particular case. While over here, it really doesn't matter which way you go, that OH group is going to end up at carbon number 2 if you went left to right or right to left, and that is what is known as 2-propanol. So in this case, because the OH group has an opportunity to be in 2 different locations, we do need to give the number of where the OH group is located. Once we do that, depending on which way you need to go to number it, you also need to give all the other groups there, right, the appropriate number based on what you chose. Now, we also talked about, I think last time, that you can classify alcohols as well. So for example, this alcohol here would be a primary, secondary, tertiary alcohol. This is a primary because the carbon that has the OH group is directly attached to one other carbon, and this would be a primary alcohol. This guy down here would be, it is a secondary alcohol, as again, the carbon that has the OH group attached to it directly is attached to 1 carbon and 2 carbons. That would be a secondary alcohol. And obviously, if we had something like this, this would be a tertiary alcohol, as the carbon that has the OH groups attached to 1, 2, and 3 carbons would be a tertiary alcohol. So much like how we could classify carbons, I personally, again, think it's easier just to look at the carbons attached to the carbons because it's the same number. Again, sometimes people teach you to look at the hydrogens that there are, but if you look at the carbon to the carbon, it gives you really the number of it is the same as the primary, secondary, tertiary. Speaking of common names, that is 2-propanol, which is technically the IUPAC name. If we condense down this sort of formula, we have something like this. Perhaps you might recognize this group. That is CH3CH3. That is the isopropyl group, and that's why this is also sometimes referred to as isopropyl alcohol, right? Also known as rubbing alcohol as well. All 3 of the same thing. So this is sometimes also called isopropyl alcohol, more of a common name. Even more common name is rubbing alcohol. So all 3 of those things is this guy right here. And again, like I said, in organic chemistry, the same thing could have a bunch of different names depending on what you look at. So for us, you should probably roll with 2-propanol, but you should also recognize it as isopropyl alcohol, because that is obviously, you might have some in your medicine cabinet, right? So that's obviously used a lot still today and stuff like that. Any questions on classifying alcohols or naming them? Obviously, if we had other groups attached, again, we would want to give those groups in alphabetical order with the appropriate number. So let's take a look at one there. I think we had, right? Yeah, let's do that. All right, so why don't you take a second here. What is the name of this guy? And let me just draw a weird one here. I don't know if it's weird or not, but I'm just gonna rando draw. See how I do. Why don't you also give a name of this one as well? I'll try to figure out what I just drew. All right, let's take a look and see. So once again, we're going to be looking for the longest carbon chain. On the top one here, I think you have 2 options. You can just go straight across 1, 2, 3, 4, 5, 6. You could also start up here if you like, come down 2, 3, 4, 5, 6 to the right. So you get 6 if you kind of did that move as well. Since we got sort of the same no matter which way we go, I'm just going to take the kind of straightest way. We also should hopefully see our OH group there, which tells us it's an alcohol. So that is 6 carbons, which is based off of hexane. And it then needs to become hexanol, OL, right? Do I need to give the location of the OH group? I do. And you could probably see that numbering right to left in this case will do the job. 1, 2, 3, 4, 5, 6. Obviously, if we numbered the other way, we're looking at carbon 5 for our OH, which obviously is a larger number. So we always want the smaller. So that's going to be a 2-hexanol for the location of the OH group. And because we sort of locked the numbering in going right to left here, that means that the other group that is there has to be locked into number 5. And that would then be a 5-methyl 2-hexanol. Any questions on that one there? All right, so what I drew here looks like hills. We got 1, 2, 3, 4, 5, 6, and 7 there. That looks like the longest carbon chain there. That obviously contains the OH group as well. So 7 is going to be based off of heptane, and then this will then be heptanol in this case. This way I should number to give the OH group which way, left to right or right to left? Yeah, this way here, 1, 2, 3. Obviously, if you want the other way, bigger than 3, right? 4, 5, 6, and 7. So that's going to be 3-heptanol. That means I locked in my numbering, and my bromine has to be at carbon number 4 in this case. And that's going to give me a 4-bromol 3-heptanol. Any questions on those there? Okay, let's take a look, see how you're doing. We'll start with, why not? We'll start with A. You could just number straight across there, going left to right, and it should get 1, 2, 3, 4, 5. The other option would be you could also, obviously, you could come this way and then turn whatever way that turn is, and have 1, 2, 3, 4, 5. Again, no matter which way you go there, you're going to end up with 5. By the way, you could also start this way and then go up if you want. So 5 seems to be our longest chain. Remember that it does need to contain the functional group here, which is the alcohol group here in this case. So we'll just take the straightest chain here. So that is 5 carbons. It has an OH group here. So that's going to be based off of pentane. And since it does have 5 carbons, I'm just going to write it underneath here. So that's going to be pentanol, right? We do need to give the location of where the OH group is located because there is basically more than 3 carbons here, 3 or more carbons. You could probably just visually see that if you go right to left here, that is going to give your OH group, again, the smaller number. And that is really the goal here, is to give that OH group the smallest number possible. That means that our OH group here would be at carbon number 2, and that's 2-pentanol. Because we locked the numbering in, we got a number in this direction for the one group that's attached, which is our methyl group, and that would be at carbon number 4. So that would be 4-methyl 2-pentanol for A there. Yeah. Any questions on that one there? Yeah, question or no? Questions? Okay. Look at the bottom one. We actually have our friend here we've seen a number of times today. That's a benzene ring with an OH group. So that's going to be phenol, right? So that is going to be our phenol there. That means that this carbon here does need to be carbon number 1. And I think going counterclockwise there will give our bromine the smaller number. We could go the other way, but that will give it a larger number. So this is going to be something like 3-bromol phenol in this case. Any questions on that one there? The one I drew up there, the line structure action, looks like we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, and 7 carbons. And that looks like probably it's going to be the longest carbon chain there. I don't think you're gonna get any longer. So 7 carbons based off of heptane, and because it is an alcohol, it'll be heptanol, OL. We do need to give the location here of the OH group, and again, you could probably just see that if you go this way, this will give your OH group the smaller number, so that's going to be a 2-heptanol. That means at carbon number 3, I have a bromol group, right? And at carbon number 4, I have a methyl group. That's a lot of groups there. We're going to go alphabetical here. So this is going to be something like 3-bromol, 4-methyl, 2-heptanol. Location, location, location. Yes. Any questions on that one here? So again, once you lock in which way you're going to number that OH group, all the other groups has to be numbered the same way. And again, the goal here is to give the OH group the priority and the smaller number. Any questions on any of those names there? Okay, then let's draw a few of these here. So drawing for these guys works the same way as drawing for everybody else. We're still gonna roll backwards, basically. So we still want to roll backwards in the name. And leave yourself some room would be good to do. But we'll just go this way. So pentanol, the penta part means that is 5 carbons. So that is what I should write here. I'll just go down here. 1, 2, 3, 4. I'll go this way. 5. Takes care of that. 2-pentanol means that my OH group is at carbon number 2. And once again, since you're drawing it, you could go either way on that. I'm going to call this carbon number 1, which means my OH group will be here on mine. Obviously, if you did number 1 on the other end, your OH group would be 1 in. That takes care of that. Because I locked in kind of going in this direction, that means that carbon number 3, I would have a ethyl group, basically a 2-carbon group. And everything else, just like normal, is going to be hydrogens until we have 4 bonds. So I need 3 there. I need 2 there, just 1 there, just 1 there, and I need 3 there. Any questions on that one there? Again, if you're going to do more of a line structure, you do the same thing. You would start with your 5 carbons, 1, 2, 3, 4, and 5. You would go to your second carbon, put the OH group, and then in this case, 1, 2, 3, is that where we had it? Yep. You would do your ethyl group there, and there you go. Yeah. Any questions on that one there? Coming here, this is cyclohexanol. Cyclohexanol is based off of cyclohexane. So that is a 6-carbon group, right? It needs an OH group on it to make it cyclohexanol, right? So that is that part of the name right there, cyclohexanol, based off of cyclohexane. 2-methyl means that this OH group definitely needs to be carbon number 1. And in this case, you could go left, you could go right, it don't matter. And just lay yourself up a methyl group right there. And there you go, in that case, yeah. Any questions on that one? Again, I drew more obviously a line structure there. We don't really need to put the hydrogens in on this particular one. Lastly, we have our friend propanol, which is based off of propane, which is 3 carbons. So maybe I'll fit it in here. 3 carbons. OL means it's an alcohol, and 1 means that this is actually a carbon number 1, the OH group, right? That means at carbon number 2, there is a chlorine group. And the rest is going to be hydrogen. So we'll need 3 there, we'll need 1 there, and we will need 2 there in that case, yeah? Line structure, something like this. With an OH and a chlorine, right? Any questions on naming or drawing alcohols? By the way, this alcohol here is a primary, secondary, or tertiary alcohol. It is a secondary alcohol. The carbon where the OH group is attached to one carbon, two carbons. This would be a secondary. This guy, primary, secondary, tertiary. It is a secondary as well. That is the carbon that has the OH group. Carbon there, one, and carbon there, two, right? This one would be. I think I heard somebody whisper it. It is primary, I think was the whisper perhaps. And that is the carbon that has the OH group attached to one other carbon right there, yeah? Any questions on those there? All right, so as we talked about ethanol, which is sometimes referred to as ethyl alcohol, is the alcohol of alcohols, right? So you get that from a little fermentation of glucose. Get some alcohols. Yeah, there you go. It's produced by reacting ethane with water or ethene with water. And again, you'll make that ethanol. And this is our hydration reaction, as we just talked about, basically. So again, we do our hydration reaction. Double bond becomes a single, and we add our OH in this case to one and our hydrogen to the other. This again is one of those cases where it wouldn't matter where you put the hydrogen or the oxygen, you will still end up with ethanol in this case. It's used as a solvent for perfumes, varnishes, and in some medicine as well. 1, 2, 3, propane triol, which is also known as glycerol. It is also used a lot it's obtained from oils, fats during the production of soaps. It has 3 polar groups. By the way, when you have more than one OH on an alcohol, the more OHs you put up there, the more soluble something like that is going to be in water, because everywhere there's an OH group, it allows it to interact well with water. So it increases the solubility of it a lot as well. Ethylene glycol is used as antifreeze in your car, and again, it basically functions to do 2 things for your car. It typically will raise the boiling point of water in your car so you don't overheat, and it will actually lower the freezing point in case you live in a really cold environment like this classroom, and you will not freeze to death, and your car will not freeze all the water in there. So a much lower temperature will start to freeze. This is PBA used for plastics and stuff like that. Again, it has our OH group, which makes some alcohols here. Now, let's talk about some other reactions that alcohols undergo. So obviously, we make an alcohol by what is referred to as a hydration reaction, which is adding water. Not surprisingly enough, we basically get rid of an alcohol by what's known as a dehydration reaction. So it's kind of the opposite reaction of the hydration. So in a hydration reaction, we take a alkene, as we saw, and we add water to it, and we get our alcohol. So again, we go from ethene to ethanol. Now, the opposite of that is instead of going from an alkene to an alcohol, you do the opposite. You go from an alcohol back to an alkene. So we take water out just the way we put it on, in a sense. And when we remove water, what we put back is the double bond. So when we put water in, we get rid of the double bond to put the water on. When we need to take the water off, we take the water off and then pop our double bond basically back in. So here, what's going to happen is an OH and an H. They also are never from the same carbon. So again, always opposite carbons. Just like you put it on an H to one and an OH to the other, you take it off the same way. Those 2 guys come off, makes our water, and now right there where we removed the water, we need to put our double bond back in. So it's basically the exact same reaction. Sometimes they will use a acid and heat, which is sometimes symbolized with a triangle as well, to basically dehydrate and take the water out. Now, there is also a similar rule that we follow, how we determine, for example, what hydrogen to take. And what I mean by that is if you had an alcohol, say like, we'll do this guy here maybe. Yeah, that, and just do this here. So when we would take off, say on this guy here, and we heat it up and we do a little dehydration, we definitely are going to take out the OH group here. But the difference here is we actually have a couple of options as to where we could remove the hydrogen. There's a carbon to the left and there's a carbon to the right. So in this particular case, we could actually choose a hydrogen off of one of those two carbons. And if you remember, when we put on the hydrogen, it ends up at which carbon? The one with the most or the least hydrogens? When we put on the water and the hydrogen, it ends up at the one with the most. When we have an option like this where there's different numbers of hydrogen, the carbon here on the left has 3 hydrogens, carbon on the right has 2, right? 1, 2, 1, 2, and 3, basically, yeah. When there's an option like this where we are going to remove water, we actually will choose the hydrogen off of the one that has the least when we're taking it off. So we would actually remove a hydrogen off of this side since it has the least. And by the way, that is where my double bond would basically end up, where I remove the hydrogen and the OH. So in this case, we would end up with this. Double bond goes in and a CH3. And then obviously we get our water that comes off in this case. So when we put on the hydrogen, it goes to the carbon that has the most. When we need to remove it, if there's an option or difference, we take it from the one that has the least. Any questions on that one there? Obviously, if there is no difference, you could take it off of whichever one you want. So again, if you had something, say like this here. So if you had our 2-propanol here. And again, you heated this thing up. We will definitely take off the OH here. Now we go to the carbon on the right. It has 3 hydrogens. Carbon on the left has 3. It doesn't matter which one you take the hydrogen off of in this particular case. So if you wanted to, you could take the hydrogen off of there. Once again, nothing else changes. Everything stays the same. Except in this case, you do have to remember that you are going to actually be putting back in the double bond when you do that, and you will get water that will come off. So in this case, you could also remove the hydrogen on the left there, and if you did, the double bond would end up over there. Any questions on that there? Okay. All right, so now that we talked about how you make them, how you get rid of alcohols, let's talk about the main reactions that alcohols undergo, which is oxidation reduction reactions. So we talked about oxidation reduction reactions previously, and a lot of times we talked about it in terms of electrons. And remember, oxidation basically means that you lose electrons. Reduction means that you gain electrons. Now, here in organic chemistry, there's not a lot of electrons following and seeing what's happening for our purposes here. So we actually use the other couple of definitions for oxidation and reduction when we're doing organic chemistry. So oxidation also means that you gain oxygen as you go from reactants to products. So if you look at something on the reactant side to the product side, it will gain oxygen. Another definition of oxidation is something that will lose hydrogen, H2, as you go from reactants to products. So in organic chemistry, these are pretty much the two definitions that we look at when we're talking about something going through an oxidation reaction. Similarly here with reduction, it is something that will lose oxygen as it goes from reactants to products is a definition that we look at for reduction, and gain hydrogen as it goes from reactants to products. So once again, these are really the two sort of definitions that we use for reduction reactions in organic chemistry and oxidation reactions. Any questions on that? So as it says there, oxidation will increase the number of carbon-oxygen bonds by the addition of oxygen and the loss of hydrogen. And again, will basically reduce the number of bonds between carbon and oxygen on reduction. So let's take a look at alcohols and sort of these reactions that occur. And they are based on the type of alcohol you're dealing with. So if you are dealing with a primary alcohol, if you take a primary alcohol and you put it through an oxidation reaction, by the way, that is sometimes the symbol that is used to imply oxidations occurring in this case. What is going to happen is you will actually oxidize this to a new type of organic compound. So let's take a look at a primary alcohol and see how this works. So we'll take our friend here, perhaps some ethanol, and I'm going to draw out all the bonds so you can see where everybody ends up. All right, so I'm going to take ethanol here. It's not an E like that. Ethanol. There we go. And again, it is a primary alcohol because when we look at this carbon, it is directly attached to one other carbon, and that is the carbon that has the OH group. So this is a primary alcohol. The actual definition of what is going to happen in this particular oxidation of a primary alcohol is the oxidation definition of we are going to lose H2. We're going to lose H2 is basically what's going to happen. And this is how it always happens in this type of reaction. Surprisingly enough, one of the hydrogens that you're going to lose is always the hydrogen that's on the OH group. So the hydrogen that's attached that makes it the OH group, that is one of the hydrogens that you remove. Where does the second hydrogen come from? The second hydrogen comes from the carbon that's attached to the OH group. You can take out either one. I'm going to say this guy. We're going to take out one of those. Again, we do not take the hydrogens from the same location. So just like when we kind of remove hydrogen from two carbons and make a double bond, this is how we remove it. By the way, at this point, everything is exactly the same. So don't get creative with it. Just copy what's there, which is I have a hydrogen, I have a carbon, I have a hydrogen, I have a hydrogen, I have a carbon, I have an oxygen, I still have a hydrogen. And by the way, my two hydrogens that came off make H2 that pops off basically here. Now, when we have an alkene, right, or an alkane like this, and I decide that I want to remove a hydrogen from both of those carbons, what do I put in between those carbons once I remove the hydrogen? Yeah, a double bond, right? So basically, if I remove those hydrogens, I end up with a double bond right there where I removed them. What should I put between the oxygen and the carbon that I removed the hydrogen? I should put a double bond. Works the same way. Yeah, you lay up yourself a double bond there. So you will make this guy right here We put a double bond between the carbon and the oxygen where we remove the two hydrogens from. And you get a new organic group right there. This is what is known as an aldehyde. So if you oxidize a primary alcohol, you will get a aldehyde. Any questions on that there? By the way, with the aldehyde, as we will see shortly, if you oxidize it one more time, we actually get the other definition of oxidation, which is we gain oxygen. And where the oxygen is gained is right there. You'll actually just put an oxygen right there. Everything else stays exactly the same. You will end up with this guy, which again looks exactly the same down to the double bond. The only addition is I'm going to pop me a alcohol, an O there, not an alcohol. And this makes another organic compound, which is known as a carboxylic acid. So if you take a primary alcohol and oxidize it once, you get an aldehyde. If you continue to oxidize that aldehyde one more time, you get a carboxylic acid. Any questions on those there? These are all oxidation reactions. Now, if we had a secondary alcohol, let's take a look at what happens with our secondary alcohol here. So if we take a secondary alcohol and we oxidize it, let's see what happens with that. So let's draw a secondary alcohol here. Let's do by the way, what is the name of that secondary alcohol I just drew? How many carbons does it have? 3. 3 carbons is based off of propane, right? That's propanol. And the OH group is located at carbon number 2. That is 2-propanol, yeah? Also known as isopropyl alcohol. Also known as rubbing alcohol as well, I suppose, yeah. That is a secondary alcohol because when we look at the carbon that has the OH group attached to it, it is attached to 1 carbon and 2 carbons directly. And that makes it a secondary alcohol. So if we take the secondary alcohol and we go through an oxidation, surprisingly enough, it works the exact same way, which is we take a hydrogen off of the OH and we take a hydrogen off of the carbon that's attached to the OH here. And once again, at this point, everything else stays the same. So we're just going to redraw it here exactly the same. We got an H, a C, an H, an H, a C, an O. We got a C, an H, an H, and an H. And obviously our H2 comes off, right? And what should I do between the carbon and oxygen? I should put a double bond, right? To make sure everybody has the right number of bonds. By the way, usually not drawn a lot of times in organic chemistry. That oxygen up on top still has like normal, it's kind of 4 electrons there to give it its 8 electrons that it has. But a lot of times in organic chemistry, for simplicity, they sometimes won't put the dots in there, but they're still actually still there, just so you know. And they're also still here, obviously, on this one here with our aldehyde as well. But again, usually not drawn in there. This makes us a secondary alcohol, and we end up with what is known as a ketone. That is a ketone in this case, where you oxidize it. The functional group of a ketone is this one right here, 3 carbons in a row with the double bonded oxygen in a center is your ketone. So if you oxidize a secondary alcohol, you actually end up with a ketone. in this particular case. By the way, as we will talk about, you actually any further than that. You can't continue to oxidize this guy any further at this point. So it won't go any further than that, unlike the aldehyde that we saw there. Any questions on that one there? Yeah, yeah. With the oxygen. Yeah, so pretty much in this situation, when we remove those two hydrogens, you need to place the double bond between the carbon and the oxygen to kind of make up for the two hydrogens that left. So it's very similar to what we were talking about with the alkane. With hydrogens, we got to kind of put the double bond in. And now when we remove them here, we have to put the double bond in. Even though it's not between two carbons in this case, it will always be between the carbon and the oxygen, basically, you remove those hydrogens. Otherwise, again, if you don't do it and you leave it single bonded, basically the carbon and the oxygen both will be short electrons. It won't have the octet rule, right? So it'll be kind of short in that case. Other questions? All right, so let's talk about a tertiary alcohol. So if I take a tertiary alcohol and I go to oxidize it, and let me just draw one here. I'm going to do a little OH action, maybe something like this. All right, and I want to oxidize this guy. Now, what do I need for this first oxidation? I need to remove how many hydrogens? 2. One should be from the oxygen, right? The other hydrogen should come from the carbon. Does the carbon in green have a hydrogen? It does not. That's problematic because it does not have a hydrogen. Or maybe it's not problematic. Maybe it's just the best one of all. You get a no reaction basically that occurs because it is missing the second hydrogen that's needed there. There's no hydrogen on this carbon, so it cannot go through an oxidation reaction at this point. So if you oxidize a tertiary alcohol, good luck. Nothing's gonna happen. You're gonna get no reaction. And so again, these are the three main type of reactions that these alcohols undergo. Primary alcohol, you could oxidize it to an aldehyde. That is the removal of two hydrogens. You could then take the aldehyde and oxidize it one more time to the carboxylic acid. That's the addition of the oxygen. The secondary alcohol, removal of the two hydrogens, will give you a ketone. No more oxidation after that point. And lastly, our tertiary alcohol will not oxidize because, again, it's missing that second hydrogen that is necessary for that reaction to take place. Any questions on that? By the way, in case you're not sure, if you go in the opposite direction, that's the reduction reaction here. You put the hydrogen back on. So just to show you how that works, if we took that guy, I had this guy, I think. And let's just say we wanted to do that reverse reaction. We're going to add the hydrogen back in, basically, right? You could imagine that perhaps it adds in exactly where you remove it. So again, it's going to be the functional part that's the most important thing here. This would be the reduction reaction that's happening. And we cannot add it in the way it is because they have too many bonds, right? So just like we get rid of the double bond to put two things in, we get rid of the double bond here and everything stays the same. And if you put that hydrogen back in, make that into a single bond, you could pop a hydrogen there. I'll just circle it, and you can pop a hydrogen there and you get your alcohol back. So that's the reverse reaction of the oxidation reaction, which is the reduction reaction. You put the hydrogen back on. So reduction in that way, oxidation if you started with that and went in the other direction. So again, they're opposites of each other. You put the hydrogen back on where you took it off from and make it back to a single bond. Any questions on that one there? By the way, you could also do that with the aldehyde. If you put the hydrogen back on the aldehyde, you will get your alcohol back, your primary alcohol back. Any questions? All right, so you're going to draw some products now of some made up reactions I make up and hope for the best. Let's see here. All right, so take a look at some and see what we will end up with. Let's see. Let's do huh. Hmm, hmm, hmm. Let's do let's do this and a little oxidation. Let's do let's do this with an oxidation. Let's do this guy with a little bit of heat. Maybe some acid. All right, so draw the products you should get out, please. Okay, so let's take a look. So we're going to do an oxidation here. So you might want to identify the type of alcohol we're dealing with. So that guy is attached to one other carbon. So this should be a primary alcohol. So remember on these oxidation, we're going to lose H2. And it always comes once again from the hydrogen on the oxygen. And again, hydrogen off of the carbon that's attached to that OH group. And it doesn't really matter which one you take. So I'm just going to take those two. Once again, when we go to draw this, everything's going to be basically the same. Nothing's going to change. So I'm just going to copy what I got going on over there, which looks something like this, I think. And I got this. And I got this. And I got this, and again an O, and I got one H. I also have obviously a couple hydrogens coming off. And the last sort of finishing touches here is we can't leave the carbon oxygen like that, so we will need to add our double bond in there, right, to kind of fix it up. Again, not usually drawn, but that's what gets everybody to the octet rule with obviously those double bond, those non-bonding electrons that are present. Once again, we go from a alcohol, which this guy is 1 carbon, 2 carbons, 3 carbons, 4 carbons. This is 1 butanol, right? As it is 4 carbons based off of butane. The OH group is at carbon number 1 in this case. This brings us to this guy, which is again an aldehyde. In case you're curious how you name this guy, that is 1, 2, 3, 4 carbons, also based off of butane. This is what is known as butanal, Al, not OL. So Al for our aldehyde is how we name those aldehydes. Again, still the same deal. 4 carbons, butane. Drop the last part, put Al at the end of it. Any questions on that one there? This alcohol here, which is a cyclohexanol, right, as it is there. This is a secondary alcohol, right? It is a secondary alcohol because that is the carbon that's attached to the OH group, and it is attached to 1 and 2 other carbons, so that makes it a secondary alcohol. Doesn't really matter. We're going to do our removal of our hydrogens. Also a reminder that although it's drawn in line sort of structure here, there is also a hydrogen that is right there on that carbon, right? There is a hydrogen that's hanging out there. And that's a kind of an important one in this case because we're going to remove our hydrogen from our oxygen. And since that is the carbon that's attached to that, that would be the other hydrogen of where we're removing it from that carbon that's there. Clearly, nothing's going to change here. It's still going to stay a ring. Once again, it's not going to open up or do anything funky like that. I still have my O, and between my O and really my carbon that's here, I need to put a double bond, right? So we'll have something like that, yeah, going on. That again takes us from a secondary alcohol to a ketone. In case you're curious, for a ketone, ketone ends in ONE. So this is cyclohexanone. Yeah, ONE. Cyclohexanone is what that is. So again, that is how you would name, for example, the ketone that's made. Any questions on either of those two? The last one is also an alcohol here. 1, 2, 3, 4, 5. That is pentanol. And the OH group is on carbon number 2. So that is a 2-pentanol happening here. We're going to heat this alcohol, which means heating is going to dehydrate it, right? So we're going to remove the water. So again, we remove the water the same way that we put it on, which is OH definitely is going. But now we need to remove the hydrogen from the other carbon, not the same one, right? So in this case, you have two options. Where should I remove the hydrogen from in this case? Yeah, we should remove it from the one that has the least number of hydrogens, which would actually be the guy on the left there. So nothing's going to change. We'll have our CH3, we'll have our CH2, and if you want, you can either write CH as that's where we're going to remove the hydrogen. We will still have our CH and our CH3, but now we need to put a double bond where we remove those two hydrogens, or where we remove the water actually, and we will have water coming off in this particular case. Any questions on any of those there? Question on reactions of alcohols, how to name alcohols, how to draw alcohols, how to dehydrate alcohols, and those things. So again, as I touched upon a little bit here, just to close out here on our alcohol conversation, as I mentioned before, alcohols, which obviously do have that OH group, and sometimes in organic chemistry, they'll put an R to represent some type of carbon group attached. But because it does have this OH group, which is definitely a very polar group, it has that ability, as I mentioned before, to hydrogen bond. And because of that, that solubility with water is going to be really good. So upwards of about, up to about, I would say 5-ish carbons. If you got about 5-ish carbons, that's an alcohol. You're going to find it to be fairly soluble in water. So it's going to be very soluble in water. It's going to be able to, like we saw with methanol, it's going to have really no problem hydrogen bonding there with water. Again, negative, positive, opposites attract. So it's going to have, again, no real problem interacting and dissolving in water. So those things are going to be very soluble in each other. They're going to mix. You're not going to have a problem. But when you start to build out sort of the carbon part of your alcohol to a lot of carbons, and for dramatic purposes here, I'll just draw a ton of carbons. Definitely going to way decrease the solubility there. So we'll just put an OH there at the end, and we'll just H2 these guys up. So clearly we got a lot going on here. And when we look at this particular alcohol, I don't know how many I drew. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I went 11. That's over 10. There you go. That's a lot. But on this part, of this alcohol is pretty much going to be nonpolar. And again, it's going to be nonpolar because it's nothing but carbon-carbon bonds, which are nonpolar, carbon-hydrogen bonds, which are nonpolar. But it still does have at the end here this kind of polar part. But the problem with this is it's frankly too big, and it's too big to interact well with water, and it's not going to be very soluble in water. Sometimes referred to as steric hindrance. Basically, the big part gets in the way, basically, of water being able to kind of get in there effectively enough to interact with it and make it soluble. So pretty much going to be insoluble in water, this guy, because it's basically, again, I would say around 5 to 6 carbons is where you start to see the solubility of alcohols pretty much fall off and become pretty much insoluble at that point. And again, it's because it has much too big of a nonpolar part to interact well with water. A reminder that in order for something to really be sort of soluble with water, you need to replace basically water-water interactions with similar type of interactions. And water as a whole is a relatively small molecule. So when you try to park this really big alcohol in there with its nonpolar part, that's just going to get in the way of everything. It's just not going to allow them to interact well with one another, and they'll become very insoluble. You don't run into that problem here because, again, the nonpolar part's relatively small. It's not a very giant molecule to begin with. So they're still able to interact because it has that OH group that's there. Again, through hydrogen bonding is what it is going to use. Now, because alcohols actually can interact well with water and be soluble with water, upwards of 5 or so carbons, alcohols can also react with themselves the same way. So when you have something like, say, methanol and another methanol, it is going to hydrogen bond with itself pretty well. And again, we would have negative, positive hydrogen bonding happening here. And what that's going to do is alcohols typically will have high boiling points and melting points because of that ability of it to hydrogen bond with itself. Hydrogen bonding is a really strong intermolecular force. So because it has this really strong force that it holds itself together with, it will take a lot more energy to break them apart and say get them into the gas phase, which is what happens at the boiling point. So we typically see alcohols as your winner in terms of boiling points and melting points. Definitely much higher than any alkane, alkene, alkyne that's just carbons and hydrogens. So any of those organic guys are pretty much like we've been talking about up to this point. They're just like carbons and hydrogens. They're going to have a much lower boiling point, melting points than alcohols. And that is because if you took something like ethane, this is nonpolar all day, pretty much, right? And nonpolar molecules will use dispersion forces. And if you remember, those dispersion forces are pretty much the weakest type of intermolecular force you could have. It basically needs something to occur for them to be able to interact with each other. So because alkanes basically are just nonpolar, it has no polar part to them, they can't hydrogen bond at all. Remember, even though they have hydrogens, in order to be able to hydrogen bond, that hydrogen needs to be directly attached to a nitrogen, oxygen, or fluorine to have the ability to hydrogen bond. So even though that ethane there has got 6 hydrogens, they're attached to the wrong thing. They're attached to carbon, which makes it nonpolar. It doesn't give it the separation of charge, like the positive side, negative side that's necessary to hydrogen bonds. So even though it's got tons of hydrogen and the name implies hydrogen bonding, you might just need hydrogen. That's all you need. It does need to be a specific type of hydrogen that's connected to those most electronegative elements, like we talked about in bonding, that's going to create that positive side and negative side to that bond that's going to allow it to interact well. So when comparison between alcohols and pretty much most organic molecules or compounds, they are usually always the winner in terms of boiling points and melting points because of its ability to hydrogen bond. There's actually just one thing that we'll talk about, which we actually just saw in those oxidation reactions and that is the carboxylic acid is one of the only things that could beat an alcohol in terms of boiling points and melting points. And when we get there, we'll talk why that is, but it has the ability to actually hold itself even tighter than an alcohol can, and it'll actually have a higher melting point and boiling point. But essentially, alcohol is going to be pretty much your winner in terms of if you're ever asked a question like which one has the highest melting point or boiling point, and alcohol's there, no carboxylic acid is probably going to be the alcohol is going to be the winner. Now, in terms of solubility, as I also mentioned, if you have a compound that has a lot of OH groups on it, or the more OH groups that you have on it, that actually goes to increasing the solubility of it. It will make it much more soluble, say, in water because of the presence of all those OH groups. They could hydrogen bond at all those locations. So even though it may be bigger, it has all those extra OH groups and it allows it to hydrogen bond with water. That is why we take something like sugar, right? Pretty large molecule, lots of carbons and stuff, but sugar is littered with OH groups all over it. And because it's a relatively big molecule, it has all those extra OH groups all over it. That's what allows it to be really soluble in water and dissolve, is the presence of all those extra OH groups. Any questions on our alcohol day?